Hello everyone, welcome back. And in this section we are going to see visualization of movie plots that we collected. So data visualization is a crucial aspect because you can immediately identify outliers and also get a high level overview of all the data that we have. For example, here you can see all our movie plots visualized, and you can see there are some outliers or clusters that are formed. So you can do all of these things using data visualization. Now the first thing that occurs to your mind is a movie, for example, will be represented in 768 dimensions or 360 dimensions, etc. So essentially a movie like Batman Begins will be a long 768 dimensional vector. Similarly, all the movies that we have, either Star Wars or Fast and Furious, everything is 768 dimensional vector. How do you visualize this? So in order to visualize this, we need to convert this into a two-dimensional vector or three-dimensional vector, because that's what we can visualize as humans on a 2D plot or a 3D plot. So essentially you need to convert every vector of higher dimensions into a lower dimensional vector, let's say two-dimensional vector, and you need to convert in such a way that the local as well as global structure is preserved. Why? Because let's say if Batman Begins and Dark Knight and Joker, all these movies are together, or all the Star Wars movies are together in higher dimensions, that is 768 dimensions, even you want to preserve the same thing, that all the Star Wars movies are closer together in a cluster, even in a two-dimension vector. So you need to preserve that structure, and also you need to make sure that, for example, if Star Wars is farther away from Batman Begins than some other movie, you also need to preserve the same thing. So you need to also preserve global structure to some level. So essentially dimensionality reduction is this technique of converting any higher dimensional vectors into lower dimensional vectors while preserving global and local structures. And you might confuse how this conversion exactly occurs. For simplicity, let's just assume that you're converting it into two dimensions, and those two dimensions are x and y, and how x is formed is just with some weighted combination of dimension 1, weighted combination of dimension 2. So it's just a weighted multiplication with all the dimensional values that we have for 768 dimensions. And similarly, you can have a different weight combination for y, and you'll get the dimensional vector for y. All you need to do is plug in these values of dimension 1 to dimension 768, and you'll get Batman Begins x and y vector, etc. Now how are these weights calculated? So you can use several dimensionality reduction algorithms, and the algorithms internally use, let's say, matrix factorization, etc., to split it into lower dimensions, and those weights could be obtained from the matrix factorization values, etc. So essentially mathematical operations extract these exact values, because we as humans cannot come up with what are the correct values for weights such that the global and local structure is preserved. So all this is taken care by the mathematical algorithms. You can see that any higher dimensional vector can be converted into lower dimensions using dimensionality reduction techniques. Here we are taking a linear combination of everything, but not all algorithms operate on linear combination. They could use some other non-linear combination of these dimensions as well to obtain x and y. If you want the third dimension z, you can just introduce x, y, z or z, where z is also some linear combination of these values. Let's take a brief look at what are the different dimensionality reduction approaches are. For simplicity, if you want to remember one takeaway, remember that UMAP is better than t-SNE which is better than PCA, principal component analysis. Over the years, people have developed several algorithms, and you can kind of assume that these are the three defining algorithms in dimensionality reductions that have evolved over the years. Barring some exceptions, you can generally assume UMAP is the current state of the art, and that's what is popularly used for dimensionality reduction and visualization. So just for simplicity, in order to understand these techniques on a high level, let's understand PCA, t-SNE, UMAP, and what are their main differences, pros and cons. So PCA is a linear dimensionality reduction. So like I mentioned, it's a linear combinations of the dimensions, and those weight parameters are obtained using matrix factorization methods, etc. And PCA mostly preserves global structure as opposed to local structure. You can reduce any higher dimensions into any number of lower dimensions, and the primary dimension will preserve the most data, and then the secondary dimension, etc. So in our case, perhaps you can convert 768 dimensions into 2 dimensions, x and y, or x, y, and z 3 dimensions as well using PCA. But the main thing to remember is that it's a linear dimensionality reduction technique. What that means is that here I have this image from statisticsforyou.info. If the data is linear, as you can see, just a line, or in higher dimensions a hyperplane, can separate this. And even when the data is something like this, still it's called linear, because you can use 2 lines and take a weighted combination and separate this exact points from the squares that you have here. But if the data is non-linear, as you can see here, you cannot use weighted combination of the dimensions to be able to classify accordingly, which is to separate these things. So that's why PCA is not perfect for everything. You cannot say that you can convert it into x and y dimensions while preserving, let's say, local and global structures, but you'll have only a linear combination. It might be a non-linear combination as well. By non-linear, I mean there could be a logarithm, log of dim1, log of dim2, or you can square dim1 or square dim2, or you can do any other non-linear combination, right? So most of the times those non-linear combinations are also inherently obtained using algorithms that you don't need to do anything separately. Simply put, PCA has limitations because not all the data points are a linear combination inherently if you want to preserve global and local structure. So there comes t-SNE, which is a non-linear dimensionality reductions, and it separates data that cannot be separated in, let's say, a hyperplane or single straight line. If the data is non-linear like this, it can convert these points into 2-dimensional cluster and these points into 2-dimensional cluster effectively. There is no way you can apply some linear combination in order to separate these points effectively. It preserves local structure as well. That's the advantage with t-SNE. The thing with t-SNE algorithm is there is a little bit of randomization, and you can control how the t-SNE algorithm performs with hyperparameters. So you can change different hyperparameters and get different output every time. A few years ago, t-SNE was the best performing algorithm in order to do 2-dimensional visualization, etc. But still it had some constraints. One thing is that it is slow, and it focuses a lot more on the local structure. So we need to strike a good balance between global and local structure preservation, because as I mentioned, you want to keep all the Star Wars movies still together even in the 2 dimensions, but you also want to separate them from other movies and preserve the distances as well. So UMAP is the current state-of-the-art algorithm which is used for dimensionality reduction, and it is also a non-linear dimensionality reduction techniques. How it operates is that it constructs a neighbor graph in higher dimensions and projects that into lower dimensions. So it's a graph based algorithm. and UMAP is faster than t-SNE, that is the advantage. And with parameter control, you can strike a good balance between preserving local and global structures with UMAP as opposed to t-SNE. So the biggest takeaway is that use UMAP and get started with it. And if you encounter specific use cases with your data where UMAP doesn't fit, then probably try out t-SNE. But other than that, that's the biggest takeaway, which is use UMAP to convert any high dimensional vector into low dimensional vector. Now this dimensionality reduction technique is not only just used for visualization, which is 768 dimensions is converted into two dimensions or 3 dimensions for visualization. But there are many other use cases where you want to do fast clustering of data, etc. In order to do those cluster, you can get to any lower dimensions, like let's say 10 dimensions or 5 dimensions even. So what I'm saying is that it need not be necessary that you are always converting from higher dimensions 768 to always 2D or 3D dimensions. For example, if your goal is just clustering and you want to do it at scale and fast, all you can do is convert the long vectors into a lower dimensions, let's say 10 dimensions or etc. So it is easier to operate and faster to calculate those clusters, etc. And what are the biggest advantages of data visualization? First of all, it gives a very quick high-level overview of all the data that we have. Here we are plotting all the 3600 movie plots that we collected, and you can immediately see that there are points like these and these which are kind of like outlier clusters. These are not single points. If you zoom in, you will see that maybe Star Wars movies, all those movies are present here, or some other movie series are present here, etc. So you can immediately get a good high level overview. You can automatically detect if there are any outliers, so that if you are training some algorithm or some other classifier, etc., you can remove those outliers automatically just looking at them visually. You can identify and remove those so that they don't affect your quality of the results. And you can also identify clusters and you can do similarity. For example, you can look here and probably that's all Fast and Furious movies, so you can see how many movies are together that are in the similar genre or talk about cars, etc. So you can identify clusters and similarities easily. And the fourth and very interesting thing is that you can actually visualize two different entities together. For example, you can plot all the movies as well as plot all the directors together and color code them such that, for example, let's say if you have a new movie plot, and you can just plot that along with these vectors, and you can easily see which director is closest to that movie plot, so that you can see if that director is available to direct that movie, etc. And also you can easily see which directors are closer to which movies, etc. So you can do multiple visualizations and those reveal interesting relations with the data. For example, you can do movies and directors, or you can take the job descriptions that are given out by the companies and plot all the job descriptions, as well as plot all the candidates. Then if you hover over any job description, you can immediately see which candidates are closer together. Or you can go to any job candidate and you can see which job descriptions are closer together so that he or she can apply. So you can do all these kinds of interesting visualizations. And the other thing is you can also plot, let's say, all the startups and their descriptions and all the professors who are doing research at research labs of universities, etc. And you can quickly see which startups can approach which professors so that they can collaborate and fasten the research, etc. So you can do all these kinds of interesting explorations by visualizing multiple items together, and we will see everything in code in the next section.